What specific problem does the proposed comprehensive blueprint for constructing RLMs aim to solve, particularly in the context of accessibility and equity in AI applications?
The proposed comprehensive blueprint for constructing reasoning language models, RLMs, aims to address the significant accessibility and equity challenges posed by the high cost and proprietary nature of state-of-the-art RLMs. By providing a clear and actionable framework that organizes the fundamental building blocks of RLMs, the blueprint seeks to democratize access to advanced reasoning capabilities, enabling researchers and practitioners, especially those from under-resourced backgrounds, to design, train, and deploy sophisticated reasoning models with reduced complexity and cost. This modular and flexible framework not only lowers barriers to entry, but also fosters broader experimentation and innovation across various applications, thereby mitigating the risk of exacerbating the divide between rich AI and poor AI. Furthermore, the blueprint incorporates diverse training schemes and reasoning structures, allowing for tailored implementations that can adapt to specific contexts and constraints, ultimately promoting equitable access to AI advancements.
How does the proposed method or algorithm work? Please illustrate the methodology step by step, particularly focusing on the structure of the reasoning process and how it transitions from user input to output.
The proposed method for reasoning language models, RLMs, operates through a structured reasoning process that begins with user input and culminates in a coherent output. Initially, the user provides an input prompt, which serves as the root of a reasoning structure, typically represented as a tree. This tree structure evolves through a series of reasoning steps, where each step is a coherent unit of thought that either explores new branches or builds upon existing ones. The reasoning process employs a Monte Carlo tree search (MCTS) strategy, where a policy model generates new reasoning steps at each node, while a value model evaluates the quality of these paths, guiding the exploration towards promising solutions. The process iterates until a terminal step is reached, which signifies the completion of the reasoning chain and produces the final answer to the user's query.
Can you provide a simple yet illustrative example of how the reasoning structure evolves during a task? Walk through the steps while detailing how different operators are applied within the reasoning architecture.
In the reasoning structure of a reasoning language model, RLM, the evolution during a task can be illustrated through a simple mathematical problem-solving scenario. Initially, the user provides an input prompt, such as, "What is 7 plus 5?" This prompt serves as the root of the reasoning tree. The first operator applied is the generate operator, which creates a new reasoning step that explores potential calculations, such as 7 plus 5 equals 12. Next, the select operator evaluates this reasoning step based on predefined criteria, such as likelihood or heuristic scores, to determine if it should be further explored or refined. If the step is deemed promising, the refine operator is then applied to enhance the clarity and correctness of the reasoning step, perhaps by rephrasing it to "the sum of 7 and 5 is 12. Finally, the reasoning process continues until a terminal step is reached, where the evaluate operator assesses the final output against the correct answer, confirming that the reasoning path led to the correct solution. This structured approach, utilizing various operators, allows the RLM to systematically navigate through the reasoning process, ensuring that each step contributes effectively to solving the task.
What are the theoretical or practical benefits of this blueprint compared to existing approaches in reasoning language models, specifically concerning accuracy, scalability, and cost-effectiveness?
The proposed blueprint for reasoning language models, RLMs, offers several theoretical and practical benefits over existing approaches, particularly in terms of accuracy, scalability, and cost-effectiveness. Firstly, it provides a comprehensive framework that integrates various reasoning structures and strategies, such as Monte Carlo tree search, MCTS, and advanced operator designs, which enhances the model's ability to engage in explicit structured reasoning, thereby improving accuracy in problem-solving tasks. Secondly, the modular nature of the blueprint allows for flexible implementation and experimentation with different reasoning paradigms, which facilitates scalability by enabling the development of models that can efficiently handle diverse applications and large-scale data. Additionally, the blueprint emphasizes the use of efficient training paradigms, such as process-based supervision and trace-based supervision, which can reduce the complexity and cost associated with training RLMs, making advanced reasoning capabilities more accessible to a broader range of users. Overall, this structured approach not only democratizes access to sophisticated reasoning models, but also fosters innovation and experimentation in the field of AI.
How was the effectiveness of the proposed method validated? Please detail the experimental design, the datasets used for testing, and the metrics employed to evaluate performance.
The effectiveness of the proposed method was validated through a comprehensive experimental design that involved benchmarking on various reasoning tasks, including mathematical, logical, causal, and common sense reasoning. The datasets utilized for testing included established benchmarks such as GSM-8K for mathematical reasoning, Big Bench for logical reasoning, and tubing and cause-effect pairs for causal reasoning, among others. Performance was evaluated using metrics tailored to each reasoning category, ensuring robust comparisons across different approaches. Specifically, the paper emphasizes the importance of using sufficiently large sample sizes for fair evaluations, recommending at least 200 samples per benchmark and a minimum of 500 samples per category to achieve low error variability. This rigorous approach to validation aimed to ensure that the proposed reasoning language models, RLMs, demonstrated significant improvements over existing methods in a variety of reasoning contexts.
What limitations were identified in the comprehensive blueprint for RLMs, and how might they affect the implementation or generalization of the model in real-world applications?
The comprehensive blueprint for reasoning language models, RLMs, identifies several limitations that could impact their implementation and generalization in real-world applications. Firstly, the complexity and opacity of the technical foundations of RLMs, including the intricate interplay of components like Monte Carlo tree search, MCTS, and various learning techniques, pose challenges for developers in understanding and effectively utilizing these models. Additionally, the reliance on high-performance computing (HPC) resources and the associated costs may limit accessibility for smaller organizations or individuals, exacerbating the divide between rich AI and poor AI. Furthermore, the blueprint's emphasis on diverse training schemes, such as output-based supervision (OBS) and process-based supervision (PBS), highlights the difficulty in gathering comprehensive training data, which can hinder the model's ability to learn effectively from real-world scenarios. Lastly, the need for explicit reasoning mechanisms may lead to increased computational demands, potentially affecting the scalability and efficiency of RLMs in practical applications. These limitations suggest that while the blueprint provides a robust framework, careful consideration is needed to address these challenges for successful deployment in diverse contexts.